Hi, my name is Ian Anderson,
And I'm Michael Spencer.
and we work on the Clang modules team at Apple. And today we're going to be talking about Clang modules at scale. So we're going to cover the last 10 years of modularizing Apple's platforms, avoiding module pitfalls, using the preprocessor with modules, and finally building modules. So Clang modules are importable interfaces. This is similar to the module features, the import that you see in Swift, C++, Python, and other languages. They're not the same thing as C++ modules. They're pretty similar, but they predate them by about 5 years. They were designed for Swift to interact with existing C code, and they can also be used from C and C++. They're defined in module map files and comprised of headers. And they build as independent translation units. And this one's pretty important. We're going to come back to that several times. So the original modules were made alongside Swift 1.0. Most libraries got their own modules. It was pretty straightforward. But once we got to user include, we just made one big module for the whole thing, and then another one for the Clang headers, and another for libc++. That didn't work, it caused a bunch of issues, but we just made some compiler kludges to shortcut some of that header module map work that we would have to come back to later. We'll talk about this a little bit more in detail. Once Swift 1.0 shipped, the library owners took possession of their modules, and we had some early adopters to start using modules. So we quickly found that modules are pretty unintuitive for C developers, and there's some pretty easily hit pitfalls there. We discovered a wide variety of contents and uses in headers, and we also found that build performance is actually not really a given. So before I jump into some specific module pitfalls, we need just a little bit more information about modules. So modules are precompiled and reused. They build as independent translation units, like we said. Include statements are translated to module imports, which is an important point, because modules do not inherit the preprocessor environment from the includer. And this is a pretty big departure from C and is actually the source of many of these pitfalls. And then finally in Swift, the module name is part of the identifier for a declaration. So that means for declarations with the same name, if they're in different modules, they are distinct types and type merging does not apply. So the first pitfall is that you need to modularize your headers in dependency order or bottom up. That means that modular headers can only include other modular headers, which we didn't follow at first, and we found that non-modular includes end up causing a whole lot of bugs that are super confusing and really hard to figure out. Some of them are that include doesn't seem to do anything. You get these weird type redeclaration errors that don't make any sense, and you also get incompatible type errors. You especially get that one in Swift. And you just get other just random errors that they don't make any sense. And so to show you kind of how easy it is to fall into that, we have an example here where we have a pretty basic module map, and that second header includes a non-modular header. And there's nothing exciting about the non-modular header, it just has a type def in it. But our unsuspecting victim at the bottom includes one of the other module headers and the non-modular header, and all of a sudden their non-modular type is a not found type. And that kind of looks like a compiler error at first, but it has to do with the way modules are implemented. There's 2 or 3 different ways you can do it, but they all result in different errors in different contexts. And there's just really no way to win except to modularize your headers in dependency order. The next kind of subtle one is that modules have to be acyclic. And that makes a lot of sense. You can't have include cycles, you can't have module cycles, sure. But it gets pretty tricky once the C standard library headers are involved, because what looks like a simple include actually ends up kind of ping-ponging between some of the search paths. So a simple include from int types to standard int.h actually hops up and down through the include nexts and the includes. And if you remember from earlier, we just originally made large modules for everything in libc and everything in libc++. And you can probably see that the module cycles are right there. So our original includes that I kind of hinted at earlier was that we blocked include from leaving the libc module, and it goes straight to standard int. But as you can imagine, this causes a lot of weird issues in C++ when it doesn't actually hop up to the C++ headers. And it also actually invites additional cycles to cause to pull in additional dependencies. And this turned out to be really difficult to fix because we just had a lot of code internally that ended up accidentally relying on these cycles. But we did finally fix it this year. And now our module maps, our module graph looks nice and linear there. So our next pitfall is make sure that your expected macros are defined. And here's where it comes out to get us, that modules built as independent translation units. So that means that headers cannot rely on the includer's preprocessor environment. So a real common case that we ran into is cdefs.h is needed by just about everything, but sometimes you forget to include it and you get away with it because just about everything else includes it, and so your macros and your basics types are there. But once you're building in an independent preprocessor environment, it suddenly becomes very important to include what you use. So that was pretty easy. The confusing one, though, is that user-provided macros now need to be passed on the command line. So you have some pretty basic code that looks like this. You have this one module that conditionally adds additional API depending on a macro definition that the client passes in. And usually you define it, you include it, and there it is. Seems like you're fine. Except in modules, you're not fine, and your function isn't found. And the reason this is because our cool module here, built on its own, where equip sunglasses wasn't defined. So the fix for this is pretty straightforward. The client needs to pass that macro on the command line, and now every translation unit sees the declaration, and we're cool. So next one, pretty straightforward. One definition rule is pretty much every one definition rule you've ever heard. Same thing. You can only have one definition of all types, macros, functions, what have you. Sometimes you can kind of cheat where it's awkward or inconvenient to do this by using if and def. Guess what's coming up? Modules built as independent translation units. So this piece of code that we used to have from Apple's copy of ICU used to have the U-break iterator defined in it, or declared in a couple of different headers, and now this is a type redeclaration error. The fix is easy enough. You just have to pick one or the other header to own it, or if it doesn't make sense for one to include the other, you just add a third header to hold some of those common types. But that's another thing to be aware of. The next one is that undef can get you into trouble. Sometimes we use it to fix other headers, so we do this in Clang itself, or float and limits.h, like to include the system one and then undef a bunch of stuff and then pull it back in. But here's another friend, modules built as independent translation units. Gotcha again. And here's our redeclaration error. This one's actually a little bit trickier to fix because Clang really does need to own these. So the Apple libc headers need to become module aware, and we had to be careful to not redeclare things that Clang insisted on owning. Extern-C is pretty similar. It gets used sometimes to fix other headers, kind of make mistakes, but modules built as independent translation units. Gets us one more time. So we have this bad header that has this getAtype function, and they forgot their extern-C there. And then you have this well-meaning header that's in the middle layers, and it tries to bracket in extern-C to kind of help you out. But once again, bad header there. It builds in an independent translation unit, so it doesn't get that extern-C bracket. It's still missing. It's still a problem. You still get your linker error. This one is particularly snarly because it kind of gets you in the habit of including a bunch of headers inside of extern-C, and I showed that standard atomic.h one right there because in C++ 23, it's C++ aware, and it has a bunch of C++ atomics in there, and it gets really confused if you bracket it inside of extern-C, and you get a lot of errors, and it's weird behavior that, again, is kind of confusing, and it gets hard to diagnose. So that particular one, we saw it as such a problem that we actually treat it as an error when you're building modules in C++ mode. Oh, and just want to throw in there, you also get the same problem including headers inside a namespace brackets. But we had too many kind of messy headers in Apple, so we worked around that one with the module kludge. We haven't quite fixed them all yet, but we've been working on this one over the last few years. Which takes us to preprocessor, and over to Michael.
Thanks, Ian. So what do you do when you need to do non-modular things in your headers? So Clang module maps have a feature called textual. And so you can put textual in front of your header in your module map. And now it's basically just a normal header. And these headers don't build as part of the module. So if you import that module, you actually won't see the content of that header. And including that textual header doesn't convert into an import. So you won't get the rest of the contents of the module unless that module, unless the textual header imports the module. And these don't build as independent translation units, they're just normal headers. So there's some dangers to this. And it's similar to all the stuff we talked about with non-modular headers. You can't allow a declaration to exist in multiple modules. They have to be part of one. And so, for example, assert.h is really hard to use from modular headers, because if you ever have different values for in debug, and then you import those into a later translation unit, Clang can get very confused and will yell at you for saying, well, which assert did you mean? Now, there are some uses of this. So a very common one in the LLVM project lease and a bunch of other projects are X macros, where we have this .def file, which needs to be textual because it's just a bunch of function-like macros. And then we have langoptions.h, which is part of a module. And this is fine because it just textually includes langoptions.def. And then in that context, it creates these declarations. And so they only belong to the actual module. They don't belong to the .def file. The next one that's common is these, we call like private implementation headers. So sometimes you'll have a header that gets split up because like it's a really long header and for some reason it wasn't split up properly. Instead it's just like chopped up at different locations. And it expects to be included in the correct order and for all of it to get included. Another one is for like parallel implementations where you'll have some common declarations and then, oh, on ARM I need like this inline assembly and on x86 I need this different inline assembly. And there's a solution for this, and we make sure that they have a single includer and that they're marked as private textual. This private textual prevents other modules from including it. And so thus we can guarantee that these declarations that exist in these textual headers are only belonging to a single module. Sometimes you have headers that really actually do have a textual component and declarations that they need. A common one is this GCC style std.def.h, where you have these need macros where say like, oh, I need pointer diff t, and then it will only define the things that you need. To do this, we create a top-level textual header that handles all the preprocessor parts of this, and then we create separate non-modular headers that actually provide the declarations. Sorry, modular headers, normal modular headers, not non-modular. So here we have std.def.h, and this is a very simplified version where, hey, if you say you need pointer diff t, then I'm going to include this special implementation header that is part of a submodule, and it actually defines pointer diff t. And here we look at the module map and see that std.def.h is textual, and these other implementation modules headers are normal modular headers. So now we have all these modules. We need to build them, and you can build lots of them. But let's take a look at some basics first. So Clang compiles these modules to on-disk PCMs, or precompiled modules. They're LLVM bitcode format, but Clang ASTs and various other information. The contents of these PCMs depends on the compiler flags, like -target, your language version, and in particular -ds. This is very common to set different -ds on different source files or targets, and so you can have a lot of variation in that. A subset of the command line forms the module context hash, and so this includes all the command line arguments that could impact the AST. And because this is formed just from the command line, we don't actually know if they definitely do, we just know they could. And so PCMs for the same module with differing hashes are called variants. So we have lots of module variants for the same module. And PCMs can only safely be reused between compiles if the hashes match. It's very dangerous to try and mix hashes. Clang will prevent you, and if you override it, sometimes it'll work, a lot of times it'll crash, or Clang will give you random errors. It's pretty bad. So the initial way we built Clang modules was with implicitly built modules. And here, modules are built by each compiler process separately when they're needed. If another compiler process needs the same module, it blocks waiting for that module to be built. And if the module is already on disk, it's already built, then each Clang process needs to actually check to make sure did any of the input files to building that module change? Because if they did, then we need to rebuild. And it's really common to have different module context hashes across translation units in a large project. So you can end up with lots of variants. And this leads to slower builds due to poor PCM reuse and this duplicate verification work. So we have these initial issues, and we had some workarounds. Builds are too slow. So implicit modules just cheats. It says, those different command line options, they probably don't matter. And so we have this non-strict context hash. And so we got significantly more frequent reuse out of our implicit modules. But this does sacrifice correctness. And sometimes you can get compiler errors, you can get compiler crashes, because you can end up in situations where you have different header search paths, which resolve to different headers in different parts of the build. Maybe they're different sizes. Now your source locations are all very confusing. You can get all kinds of ridiculous results. Now, the duplicate validation was fixed by this concept of build sessions, where the builds a very minor change to the build system, where it can tell Clang, at this point in time, anything after that has already been validated. So here we have an example build. This is like Swift, C, and Objective-C code. And it's compiling some code, discovers, oh, I need a module, so let me go off and build it. Some other code, another translation unit also needs that same module, so it's going to stop and wait. And this kind of happens all over the build. And this is basically kind of what a build with implicit modules looks like. So we came up with a better solution, explicitly built modules. Here, the build system ahead of time, before it builds anything, scans each translation unit for what modules it needs, and then builds them before actually building that translation unit. And the scanner can actually detect configuration differences that don't matter, because it's actually looking at the code. And so like VFSs, header search paths, working directories, it can say, oh, that mattered or that didn't, and then unify different variants. This allows us to use the strict hash during scanning, but not pay the cost for so many different variants. And this allowed us to basically fix correctness. Like Clang still has bugs, but these random non-deterministic bugs are almost entirely gone now. Now this is more precise, so you will sometimes build more modules, but you actually did need those modules, and you were getting lucky before. So this lets us take our implicit module build from this and go to explicit, where all the modules are built beforehand. And since our build system is smart, it can schedule things and kind of pack it all together. For a more in-depth discussion of this, my colleague Jan gave a talk at LLVM Euro 2022, implicitly discovered, explicitly built Clang modules. And Artem up next is going to talk about applying this to Swift. So, performance. Building modules currently has a large overhead. This isn't intrinsic, like it's not required. This could be fixed, but that's where we are today. And lots of variants and small modules significantly decrease the scanning performance and build performance. So there's two major ways to fix this. The first is having a globally unique configuration. If you just across your entire build, and especially at larger and larger scales where you might be compiling like 100,000 source files or something, if you can have one configuration for libc across all of those, you parse libc once, or libc++ once. And it's great if you can get to there. The next is you want to combine headers both where it makes sense and where it doesn't make cycles. And so essentially you have the spectrum between a single mega module, which is basically a PCH, and one module per header. And both of these don't work well. Module per header is too slow, and single mega module has logistical issues, especially at larger scales. And so what we found is that having one library per header is the best. Sometimes you have cycles between libraries, which it's best if you don't have that, but it happens. And in those cases, we split up those libraries basically kind of minimally to break those cycles. So some takeaways. Modules fundamentally change how the CPU processor works. And this is kind of the biggest thing. We went over, we said it a bunch, repeated it here. And both internalizing this as your modularizing stuff and for your developers, just to understand the code that they're writing. We get bug reports of like, I pound defined it and included something and it didn't have any effect. It's like, well, yeah, that's how modules work. It's kind of our biggest thing. And then header layering should be done before modularization. You really want to get this right at the start. It's hard to change later. And fixing this modularization after adoption is very hard. It makes it very difficult to do incremental changes. You want incremental adoption. You can fix things like fix your SDK as you go. And basically, again, get it right from the start. And modules affect build performance. And so you cannot naively just turn on modules and expect good performance. You have to do build system work, and and if you don't have a single configuration, you need to do client work to try and reduce the number of variants. Thank you.
Thank you, Michael and Ian. We will now take questions.
Hi, so one thing I'm curious about, you've mentioned that one of the necessary changes is that if you have something that is a define, the user may have to move it to the command line, and it's kind of the user responsibility. Is there some way to provide the users automated tooling? So something like Clang tidy, for example, plugin that would warn them that they have to do that?
So there isn't anything like Clang tidy, but there's a module map feature called config macros. And so that lets the module say like which things it needs on the command line. And then if the client code has a pound define that matches any of those names, it'll spit out a warning diagnostic. So it's not quite as automatic as Clang tidy, but it'll say, hey, I see you're trying to use this macro, you need to put it on the command
Okay,
line.
so the users will still get some kind of a warning that they have to
Yeah.
Okay.
It's manual. You have to really go through every code and make sure you caught them all. And then the users have to not have 1,000 warnings so that they can actually see it. But there's something there.
Makes sense, thanks.
Hi, thank you for the talk. That's a lot of very useful information. I was curious what your current thoughts are on the local submodule visibility flag.
Yeah, so we did want to talk about LSB here. It's just like not time. We would like to be on LSB. I guess a quick explanation. So there was a little thing with submodules. Right now, for us, every submodule can see the submodules that came before it, and local submodule visibility pretends that they're actually separate modules, and so you don't see things that you don't import. And that fixes a lot of issues. There's a few other bugs around include tracking with submodules that needs to get fixed too, but it's really hard to get there. If you can start that way, it's nice.
Thank you.
And I just have one more thing. Local submodule visibility doesn't work at all for Objective-C code. It just fails to parse it at all. So that's another major reason why we can't really use it, at least at all.
Bug to get fixed.
Yeah.
Hello. Thanks for your speech. I love Clang modules. I'm so afraid if Clang modules would die by replacing with +20 modules. Would it be possible?
So I didn't quite catch the question.
The Clang modules would make it folded into C++.
So I guess at a high level, I think actually just talk about with Richard too, is what we would like to see is header units from C++ 20 modules exist because of Clang modules. Like they're supposed to be the same thing. And we would, and the goal is for that to be true. That the module maps and stuff are kind of an extension. The semantics are almost entirely the same. We think we can get them either to be the same or very close to the same. And so, like Clang modules isn't going away, but we expect full interoperability, like with as behaving as header units.
Okay, I understand. Clang modules will be alive for a while.
Yeah.
And they're going to be needed for plain C code also. So, unless at some point later C++ 20 modules turn into C modules, but yeah, until then.
I like building LLVM tree with Clang modules. So I have some idea for improvements. Okay, thank you.
Thank you, everyone. Let's thank our speakers for their talk.